brutality, my diamonds that cold. Versace trunks, I hit my backstroke. Knock on the door, she at the back row.
Welcome back to Houdini is Hip. In the previous part, we looked at destruction, but we're now moving on. So the entire series, we've actually just looked at points and primitives and kind of how to utilize them to generate dynamics and all sorts of things, right? So we started with particles. And particles are pretty straightforward. They're just points, and then we give them some rules. So move these points in this direction by this much every frame, and you end up with simulations, right? And then we looked at vellum, where you start constraining different points together, you start adding colliders to each point so that they have a sort of width to them or thickness. And then we took that knowledge of constraining points, and we used it to constrain the centroids of different pieces of geometry, and then we ran that through bullet solving. Now, in this next part, we're not looking at points anymore. We're now moving on to volumes. And this is going to be an incredibly important concept to grasp because once we've moved away from points, we look at a very different set of tools to work with volumes. The other thing is volumes, in terms of what we're going to be doing here, exist on their own as just volumes, right? But in future parts, when we look at flip simulations or fluid dynamics, we're going to be looking at combining particles with volumes, right? So we're going to have to take both understandings, the understanding that we have of particle simulations and the understanding that we have of volume simulations, and we're going to have to bring them together. So I'm going to get into the basics of volumes. We're going to go through this maybe a bit slowly at first, but we're going to pick up speed and really get into volume simulation, and by the end of this part, hopefully you know how to do that. So let's go straight into Houdini and get started. To begin with, let's go ahead and drop a geometry node. We're just going to call this volume basics. Inside of here, I'm going to go ahead and drop a sphere. So just a regular old sphere, right? And this over here, we've worked with this before. You can see that if we activate our point display, we have a bunch of points that make this up. We also have a bunch of primitives. You can see 266 points, 288 primitives. We've worked with packing that. So you pack it all into a single point, all of that. What we haven't really worked with are volumes. So to explain what a volume is, I'm first going to scatter some points, right? So I'm going to scatter some points onto the sphere right over here. And when we scatter points onto the sphere, you'll notice that it's only on the surface of the sphere, right? If I scatter a whole bunch of points like that, there's no points inside the sphere, right? It's only on the outside of the sphere. And you can even see this if I just use a clip. So I'm just clipping an axis. So we only have one axis worth of points, right? You can see that it's empty. Right. So that means that this sphere over here is only really treated as a surface. There is nothing to help us understand the inside versus the outside of this geometry, right? There's no information inside, there's no information outside. It's just this thin shell, right? That's made up of geometry. We know that these faces are pointing outwards, but we don't really know anything about, say, the inside of the sphere or how thick it is or anything like that. This is where volumes come into the picture. So if I take an ISO offset, right over here, just to the side, and I plug the sphere in, and then convert it, it'll be a bit difficult to see what's going on. But that's because this is a very low resolution volume that I've just made. So what I'm going to do is I'm going to increase the uniform sampling divisions. Now this is like the resolution of your volume. And you'll come across this often. It'll have different names and things, but just understand that by default, it's this max axis. You'll sometimes see it by size. So if your division size is 0.1, then decreasing this value will give you a higher resolution mesh. So we can go 0, 0, 1, right? You can start to see that we now have a more defined version of our volume. Again, you can go back to max axis and set this to 100 uniform sampling divisions. That's the same as 0.01, but really these are just ways to define the resolution. Another thing that we can do when working with volumes to make it easier to see what we're doing is just press D, go over to background and switch this to dark. You can now see that we have this over here. Now what's the difference, right? Over here, we have a sphere and it's just a surface. Over here, we no longer have points, right? We have one point. Now that point doesn't really exist other than as a centroid. Once again, like we did with pieces before when we were working with pieces of fracture geometry, it's really just the centroid, right? It doesn't actually represent anything. We're never going to render that point. It's just to say that this point over here contains the position. So that's fine. But what you will see over here is that we have some volumes. We have one volume, and over here you can see the name of that volume. It's just called 0, volume 0. We can give it a name. So over here, the most common name that you'll see is density. Density is just a name given to a volume that we want to be displayed as a density. And so you're going to be seeing this a lot. Houdini registers density in many of its nodes. So if it has density coming in as an input, it'll use that for things like smoke, right? If you have something else, maybe a volume called temperature, then that might be used for the intensity of a flame, right? So density might be used for smoke, temperature might be used for a flame. So these are just names of volumes. Really, they don't do anything on their own, but Houdini works with them in specific ways. And so using the common names is good practice, for example, density and temperature. We also have vel for velocity, but we'll get into that shortly. The main thing that I want you to understand is that we've gone from geometry to a volume. Now this volume actually does represent information inside. And we can see this if we just Alt-click and drag over the scatter node and plug this into the scatter. What you will notice now, and it will take a little bit longer, is that we're now scattering points into the volume. You can see how this is different from when we're just scattering onto the surface. When we scatter into the volume and then we clip it, you can see that the entire half is made up of points, right? We've scattered it inside of the volume. And this is important because we're no longer just scattering on the outside, we're now working with a volume, which has information contained inside of it. So the way that volumes work is that they're almost like a picture. So if you have an image, right, and this image happens to be made up of pixels, each pixel holds some sort of information, right? But those pixels all exist on a grid, right? You have a grid and maybe a pixel is transparent, maybe it has a value of 0, maybe it has a value of 1. Each pixel can have a value, but they all exist within the confines of a particular grid. Maybe the image is like a 1000 by 1000 grid of pixels, and every single pixel inside of there has some information. That's the same thing that we have with volumes, except in 3D. So instead of having a single flat grid where each square holds values, we now have a box, and it's made up of what are known as voxels. Voxels are volumetric pixels. So instead of a 2D little square pixel, you now have a 3D cube, right? So this sphere over here is made up of lots and lots and lots of little cubes, and each one has a value. So if we zoom in, it might become clear that this is actually kind of serrated or rough. And if we reduce the uniform sampling divisions to like 20, you can start to see that it's a very blocky sphere. And that's because this actually works in a grid, right? It's generating a grid, a 3D grid, and each little block that falls in that grid has a value to it. And so once again, we can just push this back up to 100. And as we increase the resolution of the grid, we end up with more and more voxels, so we end up with a clear picture. It's almost like having a pixelated image versus a very high resolution image. Okay, so we got the idea of volumes, right? They're these things that are just made up of little voxels, little squares of information. And in our case, we have density, and in certain places, density is equal to 1. In other places, density is equal to 0. A useful thing to actually visualize this is the slice node. Use the volume slice node over here, plug the ISO offset into that, and you can actually see exactly what I was talking about, right? So these are those little squares that make up this. And what's interesting is that I can actually drop the uniform sampling divisions, and you can see that we have a lower resolution image over here. And as we increase it, you get a higher resolution volume just like that. So all this is representing over here in this volume slice is that range of density values. Outside, we have values of 0. Inside, we have values of 1. Density over here is 1. Density on the outside is 0. Okay, cool. So what can we do with this, right? Apart from just like scattering points. We can actually put this into a solver, but I want to show you the old school way of doing it so that when you use the sub-level Pyro nodes and stuff, you understand what's happening inside of them. It's kind of important to understand this because it's going to make every other understanding that you have of simulations a lot easier and a lot simpler. So let's go ahead and drop a null. And this null, we're just going to call density source, right? Just like that. Then we're going to drop a DOP network right over here. And we're going to plug our density source into the first input. So we just have our sphere coming in, going into our DOP network. We can dive inside. There's nothing inside our DOP network. This is used to create any dynamics network that you want. You'll see that you can create like a pop solver. You can create a flip solver. You can create any solver you want from here. We're just going to use a Pyro solver. We're going to plug that into our output, and then we're going to need a few inputs. Firstly, we're going to need an object. So we're going to need a smoke object. You can also use the Pyro object, but we'll be using a smoke object over here. And then you just need a volume source. Volume source right over here. And this one is going to be plugged into the last input over there. That's all we really need. Smoke object, volume source, and a Pyro solver. The object holds all of our information. The Pyro solver works on that information each frame. and the volume source brings new information into the solver to be stored in the smoke object once it's been solved. So all we have to do on our volume source is change this over here. So over here we have input SOP. We want it to be first context geometry. That just means the first input of our DOP network, right? The density source that's coming in, that's what we're now pulling into our solver. So first context geometry, the field to match, you can see that it's already defaulted to density. This is what I mean when I say that density is commonly used all over Houdini, right? Density is the name of the volumes that you're going to be using most of the time. Over here, under operations, we can tell it that we want to add an operation. This over here is how that volume is going to be sourced into our simulation, right? So the source volume is density. That's the volume that we're bringing in. That's the name over here. So if we check over here, that density over there, that's what we're looking for. And the target field is what we want it to be translated to, or what we want it to affect, right? So you could call the source volume whatever you want, but the target field is important. The target field is density. We want density to be the thing that's affected. So we're taking density and we're feeding it into the density field. A field is just a volume that exists within this solver. So by default, density is going to be the one for smoke, as I mentioned. So we're just taking our density and plugging it into the solver's density. The operation is that we're going to add it. So every frame, we're going to add our density that's coming in into our solver. So perfect, right? We're now bringing in that density from the first context geometry. We can try to play this back, switch on the real-time toggle, play this back, and look at that. We now have this super low resolution volume being brought into this little box of ours. So a couple of things. What is this little box? This box represents the bounds of our simulation. Old school Pyro, before they came up with sparse solving, has bounds to it, right? The bounds exist, and any smoke that reaches the edge of the bounds is either cut off or bounced back into the simulation, right? It's kind of a way to maintain a particular area for the simulation, so we can actually change the size of those bounds right over here on the smoke object. By default, it's a size of 1 by 1 by 1. We can just increase the size until it's maybe a 3 cubed, something like that. Once again, play this back. Okay, so now our volume is sitting right over there. The other issue is that it's extremely pixelated, right? Even though we have this nice looking volume coming in over here, there's another setting inside of the DOP network that actually controls the resolution inside of our solver. And that is the division size over here, right? So this division size is what the solver uses. So even if you're bringing in a super high resolution volume, it'll be scaled to this resolution when it's inside the solver. So all we have to do is increase this resolution. So division size 0.2. As you can see, this one's using by size, whereas this one over here is using max axis. You can choose whichever one you want, right? If you feel like max axis makes more sense to you, switch to max axis. So let's just say over here, we have uniform divisions of 100. Play this back. And we now have a higher resolution density. Okay, but nothing's really going on, right? We just have a density that's being added every frame. Nothing's really happening. This is when we can start to look at things like shape. So if I go over to my Pyro solver, we have some options for simulation data, right? You can see that we have combustion, and this is for things like explosions. We don't really need to bother with that, so we can even disable it. And it won't really change how our simulation is running, but there's just a bunch of things that it no longer has to work with. So now we also have shape. Now, these things over here are really important for the look of your simulation. Firstly, dissipation is how quickly the smoke fades out, right? So if you think of lighting a match, when you light a match, there's a lot of smoke initially, and then it fades off, right? If that smoke didn't fade off, you would see this long trail of smoke that just goes on forever, right? At some point, it has to dissipate into the air. That's what dissipation is. Every frame, it's going to dissipate this much. So that's the one thing, right? However, we also have things like disturbance, and we have things like turbulence. So I'm going to show you disturbance first. As you can see, it causes some distortions in our smoke. And all of a sudden, our smoke isn't as boring as it once was, right? We now have some interesting movement in our smoke. And all that this is doing is it's affecting the velocity inside of our simulation. You can go over to the disturbance tab, and you can actually see that the field that it's disturbing is the velocity field. That means that every single frame, it's adding some level of disturbance to that velocity field. And this is really nice for just adding a little bit of detail to your simulation. And you can adjust this, right? If you just want a very small amount, 0.1, something like that. Very small disturbance. Okay, so another thing that you will notice is that our dissipation over here has a tab that is meant for it, right? These are the settings for your dissipation. And you'll notice that it actually uses a control field. Now, a control field is a separate field or a separate volume that does something, right? It controls a particular element. In this case, your dissipation, so how much your smoke fades out, is dependent on a field called temperature. By default, that field doesn't exist, right? We're only bringing in our density, and we're not actually creating a temperature field. So what is temperature? Inside of a pyro solver, temperature is what controls things like fire, right? If you have something that's on fire, there's going to be temperature. So if you're in an area of high temperature, there's going to be things like buoyancy, right? If a fire is very hot, the smoke that comes off of it is going to be fast rising. As that smoke cools down, it's going to slow down and then dissipate into the atmosphere. So we can actually control certain fields with temperature. And by adding temperature, our simulation gets really interesting. So how can we add that? This is where we're going to have to look at something that is maybe a bit more complicated. It's not going to be super complicated, but it is going to be a bit more involved than what we've been doing so far. So over here, we're just creating this random density volume, right? It's pretty basic. We're not really doing anything cool with it. What we can do is that we can actually take points, give them varied attributes and noises and things, then convert them to a volume, so we have a lot more control, then feed that into our simulation. So let's do that. We won't call this volume density anymore. We'll remove the name over here. So now it's just a random volume, right? Then we go ahead and we scatter some points. So we want to scatter a whole bunch of points into this volume. Let's do 100,000. And before we do that, we'll also just switch off relax iterations. The reason we switch off relax iterations is because if we keep it on, what it'll try to do is even out the spacing between our scatter. Now, we can do it this way, or we can even use a points from volume. Points from volume is the more common way of doing it. So we can do points from volume, just like this. And your sphere can go straight into the points from volume. It's actually doing the same thing, right? It's creating a volume and then it's scattering points. This one just scatters them into a grid. And so you can decrease the point separation over here to 0.01, super dense, or you can go up a bit to like 2.5, something like that, right? You can also change this to tetrahedral depending on the arrangement that you want, and then you can do something like a jitter so that they don't perfectly align to any sort of grid. Okay, so we have a bunch of points scattered into a volume. Either one of these ways is perfectly fine to do it, all right? The next thing that we actually want to do is start generating some attributes that we can then convert into a volume. So this over here, where we have the points from volume, let's go ahead and just add an attribute noise. Attribute noise. Plug this into the attribute noise, and this is going to generate a CD attribute for us. That's not what we want. What we actually want is density. So we're going to type density over here, and density is a float, right? It's not a vector, it's just got one value that defines density. Now, what we can actually do is visualize this density, because we can't actually see anything currently. So click on this over here, this little visualizer. If you don't see the color change, make sure that in the bottom right of your viewport, you have the visualization tab switched on, like that. And now we can see the density, right? It's being visualized for us. We can now make changes to this over here. And if you take a look at the visualizer, right click on it over there and click on the pencil, you can see that low values display as purple and high values display as red. So it goes from cold to warm. You can also view it as like infrared or grayscale. You can change it over here, something like that, but I'm just going to keep it as infrared. So now we can make changes to this. Let's go ahead and actually change the element size firstly, so that the noise is a smaller pattern. And then we're going to use the enable remap ramp. We're going to slide this one over here and slide this one over here. And what that gives us is a greater contrast in our values, right? You can see that we have some very low values and some very high values. And what we can then do is convert this back into a volume. So now we have this attribute called density, and it exists on each of our points. What we can then do is use a rasterize attributes, so volume rasterize attributes over here. And then the attribute that we want to rasterize is just called density. By default, it's going to make this big, ugly shape over here. All we have to do is define what size we want each point to be. By default, it's saying that each one of these points should have a scale of 1. So it will create a sphere that's a scale of 1 around each point. We don't want that. We want super small points, right? So all we have to do is decrease that particle scale to like 0.01. And there it now fits over there. Then the voxel size is very similar to this over here, where we have it by size. That's what voxel size is. So we can do 0.01 here as well. Now you can start to see that we have a density. Maybe we want to increase our particle scale so it's not so blotchy to something like that, right? And now let's plug that into our density source and then go in here. play this back, we have a noisy density. So what's the difference? In this first case, all we've done is created a single volume like this. We've given it a density attribute. Its entire density is just sort of defaulted to a value of 1. In this case, we're creating some points, we're giving it a density attribute, and then we're rasterizing the attribute. So we're converting it to a volume. So we're going from points to a volume. Once again, check over here, density over there, and it is now defined by an attribute. So if we make changes over here, so let's drag this over, you'll see that our volume actually changes. We're driving it by the values that are on the points. Some nice things to do with this is actually to do something like a smooth. Now, one thing that you will notice is that when you middle mouse on here, this one says VDB, 1 VDB. This one over here says 1 volume. VDB is just a different type of volume. I'll get into the specifics of it, but just know that it's a more efficient volume, and you can easily convert back and forth between volumes and VDBs. For example, if you want to go from a volume to a VDB, use a VDB convert, just like this. And as you can see, you can just switch from volume to VDB. So over here, it's a volume. Over here, it's a VDB. Alternatively, if you want to swap from a VDB to a volume, you could do the same thing, convert to volume, volume over there, VDB over there. So it's really not a big deal, but just understand that they are different and you want to be working with the same type as you're going along. So over here, I have a VDB. That means I can use something like a VDB smooth node right over here to smooth this a bit, right? So now it looks nicer. And then let's also just go onto our attribute noise over here and add an animation to this, right? So over time, this will now change because the attributes that we have on here are changing over time, and that's being controlled over here. So now when we feed that into the dot network and dive inside, you'll see that we have this evolving smoke, right? Now, we want that temperature attribute. And now it's really simple. We have everything in place that we need to just add attributes to this, right? We have this points from volume, so we have points. Then we have our density being added. So all we have to do is do another attribute noise, but this time work with temperature. So attribute noise, plug it in right over here. This time we're going to be going to the top over here, changing it to a float, setting this to temperature, like that. Click on your visualizer. So now you're visualizing temperature. You can see it over here. If you just right click, you can see that it's visualizing temperature. And now we can just adjust our temperature as well. Give this a bit of an offset so the two noises don't match. Change the element size and enable this remap ramp. Give it a bit of an animation, right? So now this is going to evolve over time as well. When we go over here, we now have two attributes. We have density, we have temperature. However, when we rasterize, we only have a single volume, density. It's super simple to add another volume. All we have to do is just go over here where it says attributes density and add temperature. What this will do is it will also convert our temperature attribute to a volume. So now we have density and we have temperature. This is where it starts to get really cool. Because now, if we go into our dot network over here, all we have to do is on our volume source, add another operation, right? Remember, the volume source is where we bring them in. So all we have to do is add one over here. And down at the bottom, the field that we want to fetch is called temperature. The target field is temperature. Just make sure that the spelling is correct. Yeah. And now I'm going to leave it as add, just to show you what it looks like. Add is not actually the way that you want to be working with temperature. You don't want to constantly be adding temperature to your simulation. You either want to be blending it with the temperature that exists, or you want to be taking the maximum value, something like that, right? So over here, if I now play this back, you'll notice something pretty cool. Our smoke now moves up, right? And it's going through the ceiling over there because that's where we're capping it off. And we can very easily just move that up if we want. We can just move the bounds by selecting the smoke object, moving this up, giving it a bit more height, going back to the start, playing it again. So what's happening here is that now it's taking that temperature and it's doing a bunch of extra things for us. It's using things like our buoyancy lift. So you can see that our buoyancy lift controls how much the smoke should rise. In fact, you can even invert this. You could say something like -1, right? And then any smoke that has a high temperature will actually drop. So -1. Now it'll go down, so we'll have to just adjust this smoke object, move it down over here. We can actually switch on closed boundaries, which is kind of nice as well. As you can see, the smoke drops now. So this can be useful for something like dry ice, where you just have this smoke that kind of falls. And so now we're starting to end up with some really interesting effects, right? We're now working with two fields. We have density, that's what you're seeing, and we have temperature, which is controlling things kind of behind the scenes. And instead of using an add operation, we can use a copy operation. So that will always just copy the temperature that's being brought in. Or we can use a pull. This is one that's commonly used. And we can try this one as well. And you'll see that it's a lot more subtle, but it does still work pretty well, right? Over time, you'll notice that it starts to move down and things like that. But of course, this is just kind of your preference, what you want this effect to look like. So we can leave this at add, maybe reducing the amount that we're adding. So this acts as a multiplier. So 1 times the amount being brought in. We can do half of what's being brought in, and that might look a lot better. And let's also increase the resolution over here. So we have uniform divisions of 100. Let's do 150, or alternatively switch to by size. So you'll see that it does start to take a lot longer to simulate. I'll show you some workarounds for this. One thing is that your bound size makes a big difference for this. Another thing is that you can use OpenCL, so you can use your graphics card to accelerate this. So let's do 2.5, and there you can start to see that we have some pretty good looking smoke. So I'm not going to go too much further in this part. In the next part, I'm going to show you how to actually work with fire, how to render this out, how to bring in things like velocity. We're going to be doing a whole bunch more with this. We're going to be converting actual geometries to smoke. But for this part, you can actually just play around with this. This is a lot of fun to mess around with because you can do things like reintroducing the disturbance right over here and the turbulence. You can also go over to advanced and use OpenCL, and this will speed up your simulation quite significantly. So as you can see, a much faster simulation, and it looks really good. So this is just some of the cool stuff that you can do with some very basic knowledge of volumes, right? And this looks really good so far. So we'll start looking at more advanced topics in the next part. But yeah, go ahead, play around with this and mess around with whatever you want in this file, right? These are just some really cool starting points to play around with. In the next part, we'll also be looking at some of the presets that Houdini gives, but then you'll understand the presets in a lot of detail because I've showed you these basics. So that's it, and I hope you did enjoy this part. I'll see you next time. Bye.